the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through matrix algebra, and you probably have already gone through, or hopefully have already gone through, a section on matrix operations, how to multiply matrices, all that fun stuff, how to find the inverse of a matrix, and you should have gone through the invertible matrix theorem. That is somewhat necessary for this concept. Now in this video, we're going to step into how you factor a matrix. Yes, you can actually factor a matrix. And this is kind of a gateway to different solution methods when it comes to matrix equations. You can see on the screen right now, I have this given a matrix equation ax equals b, solve. How do you do that? Well, right now we have two methods to solving a matrix equation. We can either put it in reduced row echelon form, and so you would take that matrix equation, put it in an augmented matrix, and do reduced row echelon form, or get it to reduced row echelon form, and then solve it out, right? And as the note here states, this method is computationally inefficient, but it does work for any size coefficient matrix A. And that's going to be important because it works for non-square matrices. And that's, like I said, somewhat important. Now, if you have a square matrix, then you might be in luck, because another method for solving if you have a square coefficient matrix is to find the inverse if your matrix A is invertible. You find that inverse and perform the multiplication A inverse B to find the value of x in the equation ax equals b. But as I state here, if you're never going to use that coefficient matrix ever again in any other problem, then finding the inverse of the matrix A is highly inefficient. You might as well have just put it in reduced row echelon form, honestly. So what we're trying to do now is find a method comparable to reduced row echelon form in terms of efficiency, but with the flexibility to solve that matrix equation if given several different vectors for the right-hand side. Let me write that down actually. Now, one thing I do want to mention, we're going to reference this matrix equation, the non-homogeneous matrix equation ax equals b, many times in this lecture video and the next lecture video. So I'm going to actually label it just because I want to reference it. So 2.5.1 is what I'm going to label that as. And again, I do want to drive home the point that we already know how to solve this equation. We have two ways to do it. Put it in an augmented matrix if you know that b is never going to change, and solve using the reduced row echelon form. Doing so has the advantage that you can solve this system if your matrix A is non-square. The disadvantage is if somebody comes in and changes this vector B, then we have to redo the entire process. So it's somewhat inefficient computationally. The other method is finding A inverse and computing x equals A inverse B. Unfortunately, that's only a possibility if A is square and invertible. So we're really trying to find a method that kind of is a hybrid of these two methods, reduced row echelon form and inversing, if you will. So the concept of what we're going to do is we want to prefactor our matrix. And again, it doesn't have to be square. So we want to be able to prefactor that matrix into the product of matrices L and U, where U is a pseudo upper triangular M by N matrix and L is an invertible M by M lower triangular matrix. Now I should actually spend a moment talking about what I mean by pseudo upper triangular. To me, an upper triangular matrix is a square matrix where every entry below the main diagonal is 0. Now above the main diagonal could be a mixture of zeros or not, doesn't really matter, but the main thing is that everything below the main diagonal has to be 0. And generally when you talk about triangular matrices, they are square, but not always. Some people actually talk about upper triangular matrices when they're non-square. So you might have something that looks more like this, and somebody may say, well, that's an upper triangular matrix. because everything to the left and below any pivot is 0. And that is another definition for a triangular matrix or an upper triangular matrix. So we can consider that an upper triangular matrix, although I generally like to just call that a pseudo upper triangular matrix. And then L is an invertible M by M or square lower triangular matrix. Now a visual of this will be incredibly important. So let's go ahead and make one. So we'd like to take our matrix A and somehow magically factor it to the product of two matrices, one of which is a lower triangular square matrix that's also invertible. So something like that is what L would be. It's a lower triangular matrix and it is invertible, assuming that we don't know this theorem yet, but assuming that all those elements or entries in the main diagonal are non-zero. And like I said, you don't know that as a theorem yet, but that actually would force this to be invertible. And then U is just some other matrix, which is upper triangular or pseudo upper triangular. And by the way, in this example, I'm just using L as a 5 by 5 just because I didn't want to write things down forever. And let's pretend as though A is a 5 by 6 matrix. So my matrix U has to be also a 5 by 6 matrix for the matrix multiplication to work. Notice I am not requiring that U, the upper triangular matrix, actually have a pivot in every column, because it's not going to, nor am I requiring that it has a pivot in every row. Again, it doesn't need to. So now if you consider that we wanted to solve AX equals B, which was what we were calling 2.5 number 1, we're now trading out A for the matrix product LU, X equals B, and we'll call that 252 because we're going to reference that a few times in this video. And if we can do this factorization, which is a big if, by the way, we would call this the LU factorization. Now, why would we want to do that? It just seems like we would make our lives much more difficult by taking our nice clean matrix, even though it's a 5 by 6, taking that and doing extra computations to factor. Well, here's a clarification for you. Before you get too worried, the number of operations to find the factorization of A into L times U is nearly the same as the number of operations needed to row reduce A to the echelon form U. Now remember, when you are doing reduced row echelon form to solve a matrix equation, you're row reducing that matrix. So it's almost the same number of operations as you would need anyway to start to solve the matrix. And by the way, it's just the forward phase, not the backward phase. So if you're actually going to do the reduced row echelon form for solving AX equals B requires more computation than it takes just to reduce A into its echelon form or into an echelon form. Thus, the number of operations to get to the factored form LU is the same as getting in the echelon form of this equation right here. Now, something I need to state, and you can see I have a little footnote right there. So let's go ahead and look at my footnote down at the bottom here. There is a slight issue with the LU factorization method. During the row reduction process, you will not be allowed to swap rows. There is a way around it, but I wouldn't recommend it. And while this might seem like a significant issue that you won't be able to swap rows, the reality is we could develop a workaround. To be honest with you, I don't know if I even want to develop the workaround because there's no real need to do it. There are so many other methods out there for solving matrix equations in large systems. So LU factorization is an introduction to a whole bunch of different kinds of ways to solve matrix equations. Right now, all you know to do is either put the matrix equation into an augmented matrix and do row reduction techniques, or to find the inverse of the matrix if the matrix is square and invertible. But there are many other faster methods out there. The purview of finding those is generally reserved for either an upper division course in linear algebra or a numerical analysis course. And I can tell you from experience, because my research in mathematics was really centered around developing high-level fast algorithms for solving large linear systems, that there are so many methods out there that are super fast and really neat, really neat. So it's a field that's booming. Now, before we move on, I want to be clear about something. So I'm going to scroll up here. I'm going to write a few things down. We're given the matrix equation ax equals b, and we need to find x. Very simple. We've been doing that for quite a while. What we're stating here is if we can get it into the LU factorization, in other words, if we can find an invertible lower triangular matrix L and an upper pseudo triangular matrix U, such that L times U is A, then we can solve LU x equals B instead of AX equals B. And you look at that and you say, yeah, but I've done a lot of work to find that matrix factorization LU. Yep, you sure did, and you have a little extra work in front of you, but I promise you it will pay you back. How we do so is first we solve L times some vector is equal to B. Now let me just show something here. Right now we have LUX is equal to B. Remember, U times X is just a vector. We don't know what X is, but U times X is definitely a vector. So really, if we consider it that it's just L times a vector is equal to B, we can solve this equation to find out what Y is. But the whole point is not to find Y, it's to find X. So after we find out what Y is, we'll solve UX equals Y, because remember, UX actually is the same thing as Y. We just traded out UX for Y to simplify our statement, but really solving this equation here for Y and then saying, okay, well now let's solve this equation with our newfound Y there on the right-hand side, and we can solve this for X. And you look at that and you say, God, that seems really convoluted, but I'll tell you right now, that's an upper triangular matrix right there. So solving this for X is going to be very nice if we have that vector Y, because you essentially have an augmented matrix like this. It's already set up for back substitution, or the backwards phase of the reduced row echelon process, if you would like. And I said it earlier that the number of operations, I think it was on this page, yeah, the number of operations to factor A into L times U is roughly equivalent to the number of operations in the forward phase of the reduced row echelon process. So you're going to do that no matter what with A. You're going to do the forward phase anyway. So doing that amount of work to get to an echelon form is not a waste. And now that we want to solve this UX equals Y, and we're going to do that using the backward phase, well, we would have done the backward phase anyway, solving AX equals B. So getting to a solution of this equation right here, if we magically had that vector Y, is really about the same number of operations as solving AX equals B completely. But there is, honestly, this extra little computation of what Y is. So you may think, well, man, but you got these, fine, I agree with you. You have the forward phase that will give you the LU factorization. Fine, I'm okay with that. And you're saying that the backward phase, which I would have done anyways to solve AX equals B, well, that backward phase would solve this equation. But that's only if I had Y, and I don't have Y. So you're telling me I have one extra little step in between, and that's to find out what Y is by solving this equation right here. So I'm not terribly convinced that this will be faster. And my response to that is, well, for a single matrix, it probably won't be faster. But for a single matrix with many right-hand sides, so with an equation like AX equals B, and then the same AX equals C, and then the same A, but X equals D, this method, I promise, will be faster than finding the inverse, and it will be faster than the reduced row echelon form done 3 times. And there's an extra little bonus here. That L is invertible, and there's a very fast way to find the inverse of that L. We will see in a different video. This video is mostly set up for the conversation of what is the concept of LU factorization, but I'm not going to show you how to do it yet. I want people to first see the idea of it. Speaking of seeing the idea of it, this visual might help some people. Normally we take a matrix A, multiply it by X to arrive at B. However, what LU factorization does is if, first of all, you can factor A into the product L times U, you'll take the product U times X, that will become Y, and then y times L, in fact, L times y is really what I should have said, that will become b. To undo that process, it looks like it's a faster route to undo the process along the top of this arc, right? Because unwinding b via A inverse to arrive at whatever x is just seems smart, versus unwinding b to arrive at what y is via using L inverse, and then unwinding y to arrive at what x is using back substitution, because U is an upper triangular matrix, it's ready for back substitution, or the backward phase of the reduced row echelon method. Just seems like it shouldn't be faster. So at this point, I'm just reading directly off this because I really want to drive this point home. At this point, you should feel slightly uncomfortable with the fact that we need to factor A and then use those factors to solve two separate matrix equations. To the novice, this process should sound like it would take longer than simply using the reduced row echelon method. However, the matrices L and U are triangular matrices, very special matrices. Therefore, solving 253 and 254, by the way, I didn't actually label 253 and 254, so let me go ahead and label those right now. There we go. Solving those two equations is somewhat fast. Again, you could see it right here. If U is this upper triangular matrix, then throwing on an augmented column here and a vector y, whatever that vector y is not going to take long to solve. And I promise you, solving Ly is equal to b actually is going to be a bit of a snap. Now, I did say that I'm not actually going to showcase the LU factorization method. However, I want us to take some time to talk about the number of steps to solve ax equals b versus the number of steps to solve LUX equals b. So here's the matrix A we're going to deal with, pretty sizable, right? And that vector b is our vector we're going to deal with. Again, somewhat of a large system. One thing I need to note to you, when you count the number of operations, we call them flops for floating point operations. So counting the number of operations here, there are some things that we get to take advantage of, and I'll mention them as we go through. There are certain moves that just don't count as operations. Now, first of all, just so you know that I'm not cheating and I'm not trying to give an advantage to LU factorization over normal reduced row echelon form processes, I am going to really optimize my reduced row echelon process. That is, I'm not going to divide a row by a non-zero constant. For example, I wouldn't start by dividing row 1 by -2 because that would require me to do 1, 2, 3, 4, 5, and 6 divisions. Now you may say, wait a second, but you're also dividing this coefficient by -2. But when I say I divide by -2, I immediately don't need to compute this one. I know it's just gonna be a 1. There's no computation needed. So we are really going to optimize the system by saying, I'm not going to perform any type of divisions or something like that on a row, because that's just going to create a ton of extra arithmetic. So let's set up the augmented matrix. All right, the first step I'm going to do is I'm going to go ahead and take the opposite of row 1, and I'm going to add it to row 2. And I'll take -2 row 1, add it to row 3, and take -3 row 1 and add it to row 4. And again, I'm sincerely trying to optimize the operations so that we can minimize the number of flops. So how I'm going to note this is that every time I have an operation on an entry, if it's a single operation, I'll use a triangle. If it's 2 operations, I'll use a square on it. The first thing I want to note here is that I'm doing those row replacements to force zeros below that pivot -2. There is zero computation doing that. So again, totally trying to give all the benefit of the doubt to the standard row reduction technique. All of those zeros, they require no computation at all. I know they're going to be that by design. Also, even though I'm saying take -1 and multiply it by row 1 and then add that to row 2, I can optimize that sentence and just say, you know what row 2 is going to be? It's going to be row 2 minus row 1. It's just a subtraction. So that's going to be a single operation. So again, all of those required one operation. I'll just box those up in green as triangles. I say box, but I mean triangle those up. So that's 6 operations right there. Okay, not bad. Now I'm going to take row 3 and subtract twice row 1. Now that is going to be 2 operations because you're doing an addition and you do actually have to multiply row 1 by 2. So I will go ahead and say each of these are going to be 2 operations. Let's go ahead and tally those up just to keep a running tab. 30 operations so far. Now again, full benefit of the doubt to the row reduction method here. I'll go ahead and recognize we do not need to make a pivot in that next column because there is not a pivot in the next column. And so now we're going to work on this column right here. So negative twice row 2 added to row 3 and negative 3 row 2 added to row 4. Again, those are both going to beget 2 operations each. Rewriting is not an operation, so all of that right there doesn't cost me anything. Also, we know that any values before the pivot we're working on will be 0, so these cost me nothing as well. And one final thing, we by design are killing everything below, so those cost me nothing too. So again, really trying to give the advantage to row reduction algorithm here. Let's go ahead and do the multiplications. All right, and barring any arithmetic mistakes, we've just added on, remember each of those squares is 2 operations. So let's see, we have 8 of them. 8 times 2 is 16, 16 more operations. Now let's go ahead and erase our boxes. And now we're gonna focus on this guy right here and killing everything below it. Again, it's going to be 2 operations, but everything I've written there is a freebie because none of that changes, and we are by design killing off this element right there. So we really don't have a lot in the way of computation. Let's go ahead and write it out. Not too bad. Each one of those are 2 operations, so we've added 4 more operations. Now it's at this point that I'll make the pivots 1 as I move through the backward phase. Let me first start by erasing these boxes. I will divide row 4 by 5. When I do this, I will do this again, giving full advantage to the row reduction method. That is, I happen to know that every number prior to that pivot at 5 is 0. There's no need to worry about doing any mathematics on those. Those will all remain 0. However, the division by 5 will have to strike this guy. We don't know, I mean, we do know it's 0. Obviously, we're staring at it. But in general, we don't know that that's 0. So let's just pretend that's a non-zero number and we're going to divide it by 5. Dividing this by 5 costs us nothing because we're dividing by 5 to force it to be 1. We know without doing mathematics that will be 1. And I put a green, or not green, but I put a red triangle there because again, that was only a single operation. So it only took 1 operation for that. And I shouldn't pluralize a single operation. Now to start the backward phase. We'll use this pivot right here to kill everything above. And conveniently, we're just going to take negative row 4 and add it to each of those rows. Remember, this is actually not going to be a multiplication. I can consider it as row 3 minus row 4 becomes the new row 3. Row 2 minus row 4 becomes the new row 3, and so on and so forth. We also know beforehand that there's no mathematics needed to compute this. These are going to, by design, become 0. So again, all benefits given to the row reduction method. The only thing that I will say will cost us is, even though we are technically just adding 0 to each of these, I'm going to again state, let's assume that it's non-zero because we don't know if it actually in the long run would have been. So each of those will cost us 1 operation. Looking at how much paper I have left, not very much. Maybe I'll scoot things over. We have enough room for 1 more matrix below this, so I'm going to do that. Going to the next pivot, we're going to change that, divide that entire row by 3. Again, only 1 operation needed for this move. And that's because we are dividing by 3 by design to make this a 1. So the only computation I really need to change here is this guy. And I should say it's the only number that I need to compute on. It's a single operation. Now I'll go ahead and add row 3 to rows 1 and 2, or 2 and 1 as I highlighted those. Again, by design, these two entries right here are just going to be 0 without any computation. However, we do need to use some computation for these two entries right here. And it's going to be a single operation, so I'll box those up in triangles just to say those are both single operations. You can see the number of operations actually gets fewer as you move through this process, by the way. 30 ops to begin with, and now we're really down to the kind of the bare bones. Now we focus on the next pivot, and that next pivot is actually right here. And so we're going to force that to be a positive one by multiplying that entire row by a negative. Now, when I multiply row 2 by a negative, again, by design, that entry right there, sorry, I just did it, will automatically become 1. So there's no need for me to compute. However, this is a non-zero entry. It's not above a pivot. So I do have a little bit of mathematics there. I'll go ahead and write the negative in there, but that'll cost me one operation. The rest of the entries in that row are going to be 0 by design from before. They don't get touched by our operations. However, the last one, we do have a single operation to force it to be a positive one, and so that's 2 ops. Now we'll take the opposite of row 2, add it to row 1, and really you can think of that as a subtraction, a single operation if you want to, just because, again, we're giving advantage to the row reduction method. By design, this will be 0. And now let's run the rest of it. We get down to there. Remember, each of those little triangles are a single operation, so we have 2 operations there. And finally, we'll finish this out by dividing the entire first row by a -2. And you can see we do actually have a few operations here. Now, everywhere there was a pivot below, that remains 0. The pivot in this row will, by design, become 1. So all of those don't cost me any operations. However, this does. A total of 3 operations. And we'll call that solved for now. Let's count up the number of operations. Let's see, we have 30 plus 16 is 46, plus 4 is 51, 54, 55, 55 is 57. Okay, 57 operations there. Plus the 2 is 59, 61, 64 operations altogether. And that's if you optimize the entire process. Now let's do the same thing, but assuming that we have the LU factorization. We'll start by stating we need to solve AX equals B, which is the same thing as LUX equals B. And we're going to say, well, I don't know what X is, but let's solve LY is equal to B. Let's find out what the product of U and X is. So let's solve Ly is equal to B. We know what L is. They gave us that. That's that lower triangular matrix right there. And we know what B is. It's on our previous page. So let's go ahead and set up a system to solve that. Again, there are several different ways to do this. I'm going to actually just do it as if you've never seen the upside down version of this. So let's go ahead and just do it like we normally would. I'll take the opposite of row 1, add it to row 2. And I'll take, let's see, -2 row 1, add it to row 3. And finally, -3 row 1, add it to row 4. Now, again, I'll use the squares and the triangles. Triangles for 1 operation, squares for 2. And again, giving a little bit of benefit here, the fact is we know those operations are going to zero everything out below. But we also know that row 1, because it's lower triangular, it has zeros everywhere after that first pivot. So all the mathematics after that don't cost us anything. There's no math here. The only math that I have is actually in the augmentation column. So all I had to do here, I did give myself the benefit of the doubt that really the first operation is just taking row 2 minus row 1. So it's a single operation. But otherwise, I have 1 plus 2 plus 2, or 5 ops right there for that first step. It really does super help that all of our elements in the row after our 1 they're all zeros except for in the augmentation column. So you could imagine, okay, so the next step, I'm going to take this entry right here and I'm going to use it to kill everything below, but there's actually no other math involved. I'm going to take -2 row 2 2, add that to row 3, and also take -3 row 2 and add that to row 4. When I do that, by design, these will zero out without any mathematics and nothing else changes in the coefficient matrix. These down here definitely change. So let's go ahead and do that. Each of those are 2 operations, so that's 4 operations altogether. And finally, one little rinky-dink little operation left. -2 row 3 added to row 4. By design, that'll be 0. So the only one I actually have to compute is that bottom right entry right here. That poor sucker keeps hopping back and forth between 0 and 6, but there we go. That took 2 operations. And we have the solution to Ly is equal to b. We know that y is -2, -2, 3, 0. Now we're not quite done, but you can see we had 64 operations before. We only had 11 right now. Of course, we still have to solve ux equals y, because that's what ux was equal to, and we're really trying to find x. So let's go ahead and write down the matrix U augmented with our newly found y. Now you might look at this and say, is he gonna go through all of these? Oh my gosh, I'm so bored with this. Well, no, I don't have to now, because I don't know if you noticed. You probably don't, honestly, because I wouldn't have noticed either. But this matrix we've actually seen. We arrived at it right here in our previous page. And so starting here to this point right here, we're going to start counting the operations it takes to get to the solution. 1 plus 3 plus 1, well, that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 extra floating point operations, and we'll get to the same point we got before. So again, we had how many ops before? We had 11 plus 14 is 25 ops total. And you say, well, wait a second. That's because somebody pre-factored A into the product of L and U. I bet you it took a long time to get down to that factorization. And I'm going to tell you it's the same number of operations to get down to that factorization as it is to get through the forward phase of what we started on the previous page. The forward phase is just taking our original matrix and getting it down to this point right here. And that is costly. Don't get me wrong, that is very costly. It cost us, 30 plus 16 plus 4, which is 50 operations. So I'm telling you that to get this factorization already, just like this, would cost around 50 ops. And then we just tacked onto it another 25. So you say, aha, 75 operations altogether versus the 64 you had before. And I say, yep. However, once you have this factorization, it speeds up all future computations significantly. That is, if somebody comes in the room and says, you know what, sorry, I made a mistake. That B should not be -2, -4, 5, 6. It should have been +2, -4, +5, 6. And you go, ugh, and you have to go through all of these operations yet again. You still have 64 operations to go through. Me, on the other hand, well, you did 64 before. Let me write that down. And then somebody comes in and changes the game. You have to do another 64. So you do 128 operations total. Me, on the other hand, I do 50 ops initially. And then when I solve the original system, I do an extra 25. So I do 75 total. But then they changed the B. Well, I already have L and U. A has already been factored. So these 25 ops are the same 25 ops I'd need to do if they change B. If they change this B, so that's a +2 there and a +5 there, I would just still have 25 ops. And so for me, when they change the right-hand side, I tack on an extra 25 and I have 100 total versus your 128. It gets even better for me when they change that right-hand side vector, because every time they do, it only costs me 25 extra operations versus for you, it costs you 64. So if you have 11 right-hand sides that were handed to you, you will have 704 operations. But if I had 11 right-hand sides, I would have 75 for the first one they handed me, because I'd have to get the LU factorization, and then 10 sets of 25 for all the other 10. And so that'd be 250, 325 operations versus your 704. And when you're talking large systems, these are just small systems here. This is nothing. This chump change, very small things. But real world applications, you have matrices on the order of thousands by thousands in dimension. And if you can save computational speed and time, you're making money. Because the more time you spend computing, the more time you spend on energy, the more time you spend waiting, and the more likely it is that somebody else can beat you to the punch and solve a system or get a better product out or whatever it may be. So I hope that was somewhat impactful. The recording, by the way, you guys don't know it, but behind the scenes when I record this is an hour and 22 minutes. Now, obviously, you're looking at the timer up there. It is not an hour and 22 when I am done editing it. But man, oh man, these take a while to record. So anyway, I hope this is helpful. I hope it opens your eyes to a whole universe of really, really cool methods. If you're a computer science major, welcome to it. This is exactly what you're going to be focusing on for a while. All right. Hope you have a great day. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.